primarily we're going to be talking about data and data availability, or the lack of it, really, when it comes to research applications, in particular in the defense domain. So this is just a quote that I like to indulge myself with, if you can have a look at that. Big fan of philosophy and artificial intelligence. I think they go hand in hand. So just outlines, a little bit background about what I mean by data availability and the lack of it in defense in particular. I'm going to talk about certain things that we looked at in the past at Roke as an organization and other researchers worldwide when it comes to that sort of problem and how we tackle it. Mainly talking about generative, so unsupervised methods, and also using things like transfer learning and simulation to train your models, if you like. And also there's something I've been dabbling with, especially in the last few months. It's actually based on leveraging the knowledge of the experts, really. And it's something very experimental at the minute. I've just had a kind of almost a proof of concept to convince myself I'm not doing something stupid, but I'm very, very kind of happy for your input on this, and set me straight if you like, if I say something stupid. Right, so the background here is as follows. We have a lot of, deep learning in particular has almost caused a paradigm shift when it comes to machine learning. The biggest advantage we have is the ability to actually interface with the raw data directly without having to ask an engineer or an expert to design a feature set that can interact with that data. And the data or the feature set has actually been generated or modeled by the learning process. This gives it a lot more flexibility in which to optimize the feature set and also give the machine perspective, because as human beings we like to express the world in our own understanding, and this is not necessarily the case for artificial intelligence. I remember when I was an undergraduate and going to these conferences and people coming up with feature sets and different methods, the DAISY feature extractor, the SEFT feature, whatever, all of these things. And one question what came to mind all the time: how do you know this is the right feature set for this application? It's always, how do you validate that this is the right feature set? And I think deep learning in particular answered that question for us. It really should be left to the optimization process to pick what sort of features the algorithm should design by itself. Obviously, this introduced some sort of challenges, is mainly because the amount or the volume of data required to be able to derive these features. It's because it's an optimization-driven process. You want to be able to represent your problem domain in a way that can be representative for all different edge cases. And if you're not careful, you could easily overfit things or basically cause any sort of bias into your learning process. Right. So, and just before going here, and that is precisely the problem when it comes to applying deep learning in defense, for example. It's always the case when we talk to our defense clients or customers, we have this problem, can you solve it for us? Yes, we can, but do you have the data that goes with it? Usually, maybe we have data if they could be really badly formed data, but the biggest challenge by far is the annotation that goes with that data. You can have massive loads of benign data, but that doesn't really, for example, if you're looking for situational awareness in maritime domain, having AS data all over the place for months and years, that's not a problem. Can you annotate that to identify threats and be able to train a machine learning algorithm to pick these threats up? And that is really the challenge for us. I think we can have to tackle this problem if we really want machine learning to be able to be adaptable to real life situations. As human beings, we don't really need that volume of data to learn things. And I think this is almost the next stage for us when we go to develop a new machine learning architectures and protocols. So just almost like a history of what sort of the ways we deal with that problem is using generative or unsupervised methods. So talking about AS data, I just wanted to show you and share with you some of the work we've done in the past. So this is something not really very clever. It's actually based on statistical atlases. And what it's doing is actually we have an antenna at Roke actually reading AS data coming from the Southampton waters. And over several months, the system itself, using the statistical atlas approach, start modeling what normal behavior should look like. And to do that, we can actually infer whether something is abnormal by measuring the deviation from the norm or the normal behavior. It's just a Mahalanobis distance from the multi-distribution or multi-dimensional Gaussian. So in this example here, you can actually see in a minute that there is a signal here that flares up when it says there's something abnormal happening. The system doesn't actually know what's abnormal. It just knows that that deviates from the norm. And we didn't actually give it any rules or anything. That's solely driven by data. So you can see here, even before measured deviation from the actual route, the system has picked up, this is something abnormal. You need to look at that. Just a simple deviation from the conventional track of that ferry from Isle of Wight to Southampton has been identified as something abnormal. And you can see this has actually become quite abnormal, so as this runs along. The other interesting stuff, for example, we picked up. So this is the same sort of area. And since we're only measuring, for example, AS data, actually, we are not really monitoring Mayday signals. And I think a couple of years ago, there's a tug capsize in the area. We didn't pick up this signal. What we actually picked up is the changing behavior of the ferry responding to that signal. So you can see here, so this is the ferry, just going back to Southampton. And you can see here, it starts picking up something abnormal. I think the ferry starts slowing and now start turning. It's just basically going back to rescue the tug. So, yeah. And so this is one of the things we use in order to avoid having to actually label the data, is actually learning normality and abnormality over a period of time. And this is another thing that we've done, which is a project funded by the Home Office. And there's a big problem when it comes to firearms smuggling, contrabands and drugs, narcotics and everything. It's a massive issue. So one solution is you might look into it from a computer vision point of view by modeling a 3D structure of the firearms and trying to pick this up in X-ray images, which is fine. However, you're going to have to do this for every single variation of that firearm. You have to do it also for when you deassemble the firearms. You can have to do it when the firearms, for example, deliberately trying to be hidden, which is the kind of the objective here for the smugglers. So what we decided to do is actually following the passive detection approach. I don't know if you're familiar with the stealth aircrafts. The way they detect stealth airplanes is not by actually looking for the airplanes, it's by looking at the signal disturbance around the airplane. And what we're actually doing here, we are not actually picking the firearms, we're actually picking the disturbance around the firearms being embedded within the luggage. So it's based on the same context, principle. So what we've done, we actually took a lot of benign data, which is, I thought, a lot easier to get rather than labeled data. Anything that has been scanned through the scanners over a number of months or probably years, and trying to model the normal distribution of how a luggage looks like. We humans like to think of ourselves as unpredictable. It's quite the opposite, really. We're quite predictable. And we can monitor exactly what sort of distribution a luggage could look like, and at least the contents of that luggage. So we use the variational autoencoder in order to build sort of that model. And so this is sort of the if you like, the work that has been done in terms of identifying something that does not conform to the norm. So we have the input image, we have the output, which is what the autoencoder think this image should look like, and we have the difference. And in this particular one, the interesting bit, these are actually weights that has been put in the luggage to calibrate the X-ray scanner. I think this is probably a motherboard. So this is something that has been picked up as something, I don't know what it is. So, look at that. And this is, I think, something more clear. Obviously, if you have a gun this big in your luggage, you're going to pick it up. I mean, yeah, it's just, but it's just like, it's testing the principle here. But, yeah, you can't miss that. If you miss that, we have a massive problem. But so this is what comes out from this. So this is what the image looked like. This is what the model think it should look like, and this is the difference between the two. I'm not going to go through that. So because, operators like numbers, they like to say how confident you are, we had to kind of hook up a softmax layer towards the end of it to be able to classify things, but this is not really the point. So for example here, it's always impossible to make up what's made from this, but this is a genuine threat. There's a gun in there. And things like, so there are things that are obvious to see, but there are things that are quite hard to see. And if someone working in a working environment, is constrained by time, they're bound to make mistakes, and their attention level is going to drop down. So technologies like that can help them do the job. This is some benign images, right? The other ways I said that we might actually look into to actually tackle the problem of data availability and annotation is using something called transfer learning. So transfer learning, in a way, requires labels, but probably you don't have to train it as much as a base model. It's not really a solution. It's more than a hack, really. But there's also, actually, I was in a meeting last week, DSTL meeting about the accelerator call about one of the AI human interaction challenges. And one of the companies actually presented some work to detect tanks using simulated environment. The simulated environment was a game. So basically they took a game, they used the game to take samples of that tank, and they actually trained it and then applied it on real images, and surprise, surprise, it worked. So there are certain ways you can actually, do that. And I know for sure there's some research that's been done to explore the use of GANs. I don't know if you generative adversarial networks. And this is basically, am I on time? Maybe I need to go faster. Right, so to use that in order to make it look like the simulation more like real. But right, so I don't know if I should show this. This is just a marketing material, but I don't know. I like it. I don't know if you add anything. But yeah, so this is, we know that. A lot of people actually do object recognition in defense. They try to detect things. But the advantages of having artificial intelligence in defense is immense. You can, for example, a drone like this could go in stealth a lot longer. It doesn't have to communicate with base. It can maintain its stealth. It doesn't have to use the same bandwidth. You can send text only. You can actually do subsequent procedures based on this sort of recognition and understanding. All of that necessary for us to be able to do something more exciting in the defense space. But again, this goes back to the data. So we, for example, use transfer learning on our something called a project we currently do with a company in Southampton. And this ship in particular is sailing at 30 knots. And there's a transfer learning mechanism in front of it to be able to pick objects and avoid them based on deep learning. So there's one thing that I've done a few months ago within the Information Warrior AI Hackathon in April. And this is something that I think I didn't really expect to be kind of, to see the end users excited about this that much. But for us, it's easy for us to kind of get locked within the sort of our technical bubble and trying to, strive for perfection. But sometimes things that we deem not important actually have massive impact on what they can actually provide in terms of capability for the officers in the front line. So this is something I've used, which is basically taking something like Inception, which is a Google model for deep learning, and using that instead of doing training again, use the feature layers, the bottom layers, the bottleneck layers, in order to identify things of similarities. That has been trained on the visual spectrum, but this has been applied on infrared footage from the maritime exercise, I think, Unmanned Warrior in Scotland, somewhere around Scotland. Yeah, it's just running through that. I just can skip that. So this is the image. You click on that image, and you just go and search your entire database. Could be thousands of hours, and look for anything similar to that. Again, there's no training required whatsoever. So what happens is just go and pick anything that looks similar from the video, and just brings it up as video segments to you, which should happen shortly. Yeah, different directions, different orientations. Yeah, without training. Right. Lastly, I think, so this is what I was talking about, leveraging the knowledge of the experts. in short, I think I don't really have time to go through all of this, but what I'm going to say is that, in short, I think it's valuable for us to actually leverage the knowledge of the expert at the front end and use that in order to drive our training process. So you can use something like online learning, which is something we've done here. And what we've done, basically, we took an AI module, make it sit next to an analyst. The analyst interacts with some data. This data could be surveillance data. And the way the analyst interacts with the data, it can figure out which data is relevant, which data is not relevant. And this can suppress, for example, false alarms. So the analyst doesn't need to actually look at every single alarm comes up to them. So this is based on some sort of backend model and an online learning process. You can see this is based on taking something simplistic like the OpenCV classifier, pedestrian classifier, and boosting that by using the online learning. You can see that it starts flaring up at the beginning on the both videos, but after a few frames, the model, the false alarms got suppressed on the online process. And to be honest with you, that is quite, I wasn't expecting this to happen, but this is a data set that hasn't been seen by the machine learning algorithm at all. So it basically was learning on the job, driven by the output of the OpenCV classifier, which is being put really there just to simulate the interaction of the human expert. Obviously, that one has quite a lot of errors, and this actually still works. But if you have something with more quality input, that hopefully will make it better as well. Right, so AI in defense. I encourage all of you to get involved as much as possible with these AI hackathons. There's currently one happening today, and that's why I couldn't be with you all today. I would love to be here, but I'm going to have to duck out again for the AI hackathon. And this is the MOD AI hackathon, which is happening yesterday and today. There are main 4 challenges: the Navy situational awareness, there's the information system, and support the big data, big decisions, and the defense intelligence, which is looking at satellite data, satellite images. And it's a very exciting opportunity. And whether we actually think this is something that AI has a role to play or not, or whether the culture hasn't caught up with this yet, this is happening. And I think just to bring this up, I just bought this because I like the title, AI Captain, but this is something that Roke has actually going to deploy on one of the warships, Type 23, I think. And it's currently being integrated into the system, and hopefully next year we're going to put it in sea trials. Thanks very much, everyone.